Hello everyone, this is an audio recorded lecture from class 12's NCERT on the topic coordination compounds chemistry. In the previous unit, we have learned that the transition metals form a large number of complex compounds in which the metal atoms are bound to a number of anions or neutral molecule by sharing of electrons. In modern terminology, such compounds are called coordination compounds. The chemistry of coordination compounds is an important and challenging area of modern inorganic chemistry. New concepts of chemical bonding and molecular structure have provided insights into the functioning of these compounds as vital components of biological system. Chlorophyll, hemoglobin, and vitamin B12 are coordination compounds of magnesium, iron, and cobalt, respectively. Variety of metallurgical processes, industrial catalysts, and analytical reagents involve the use of coordination compounds. Coordination compounds also find many application in electroplating, textile dyeing, and medicinal chemistry. Now, first topic in coordination chemistry is Werner's theory of coordination compounds. Alfred Werner, a Swiss chemist, was the first to formulate his idea about the structure of coordination compounds. He prepared and characterized a large number of coordination compounds and studied their physical and chemical behavior by simple experimental techniques. Werner proposed the concept of primary valence and a secondary valence for a metal ion. Binary compounds such as CrCl3, CoCl3, or PdCl2 have primary valence of 3, 2, and 2 respectively. In a series of compounds of cobalt 3 chloride with ammonia, it was found that some of the chloride ions could be precipitated as AgCl on adding excess silver nitrate sodium nitrate solution in cold, but some remained in solution. For example, 1 mole COCl3.6NH3, which is yellow in color, gives 3 mole of AgCl. 1 mole of COCl3 5NH3, which is purple in color, give 2 mole of AgCl. 1 mole of COCl3.4NH3, which is green in color, gave 1 mole of AgCl, and 1 mole COCl3.4NH3, which is violet in color, gave 1 mole of AgCl. These observations, together with the result of conductivity measurement in solution, can be explained if 6 groups in all, either chloride ions or ammonia molecule or both, remain bonded to the cobalt ion during the reaction, and the compounds are formulated as shown, where the atoms within the square brackets form a single entity which does not dissociate under the reaction conditions. Werner proposed the term secondary valence for the number of groups bound directly to the metal ion. In each of these examples, the secondary valence are 6. Note that the last two compounds in the table have identical empirical formula COCl3.4NH3 but distinct properties. Such compounds are termed as isomers. Werner in 1898 propounded his theory of coordination compounds. The main postulates are: in coordination compounds, metals show two types of linkage, primary and secondary. The primary valences are normally ionizable and are satisfied by negative ions. The secondary valences are non-ionizable. They are satisfied by neutral molecule or negative ions. The secondary valence is equal to the coordination number and is fixed for a metal. The ions or groups bound by the secondary linkage to the metal have characteristic spatial arrangement corresponding to different coordination numbers. In modern formulation, such spatial arrangement are called coordination polyhedra. The species within the square bracket are coordination entities or complexes, and the ions outside the square brackets are called counter ions. He further postulated that octahedral, tetrahedral, and square planar geometrical shapes are more common in coordination compounds of transition metal. Thus, CONH3 whole 6 3 positive is tetrahedral entity, while NiCO4 and PtCl4 2 negative are tetrahedral and square planar respectively. Difference between a double salt and a complex. Both double salt as well as complex are formed by the combination of two or more stable compounds in stoichiometric ratio. However, they differ in the fact that double salt such as kernelite, that is KCl.MgCl2.6H2O, and more salts, that is FeSO4.NH4 whole twice 2 SO4.6H2O, potash alum, that is KAlSO4 whole twice dot 12H2O, etc., dissociate into simple ions completely when dissolved in water. However, complex ions such as FeCN6 4 negative of K4 FeCN6 do not dissociate into Fe2 positive and Cn negative ions. Next topic is definition of some important terms related to coordination compounds. First is coordination entity. A coordination entity constitutes a central metal atom or ion bonded to a fixed number of ions or molecules. Next is central atom. In a coordination entity, the atom or ion to which a fixed number of ions or groups are bounded in a definite geometrical arrangement around it is called the central atom or ion. Next is ligand. The ion or molecule bound to the central atom in the coordination entity are called ligands. These may be simple ions such as Cl negative, small molecules such as H2O or ammonia, larger molecule such as H2N, CH2, CH2, NH2, or even macromolecules such as protein. When a ligand is bound to a metal ion through a single donor atom, as with chlorine, water, or ammonia, the ligand is said to be unidendant. When a ligand can bind through two donor atoms, as in ethane 1,2-diamine or oxalate, the ligand is said to be didendate. And when the several donor atoms are present in a single ligand, as in NCH2CH2 NH2 3, the ligand is said to be polydendant. EDTA is an important hexadendate ligand. It can bind through 2 nitrogen and 4 oxygen atoms to a central metal ion. When a di or polydendant ligand uses its 2 or more donor atoms simultaneously to bind a single metal ion, it is said to be a chelate ligand. The number of such ligating groups is called the denticity of the ligand. Such complexes, called chelate complexes, tend to be more stable than similar complexes containing unidendant ligands. Ligands which has two different donor atoms and either of two ligands in the complex is called ambidendant ligand. Example of such ligands are the NO2 negative and SCN negative ions. NO2 negative ion can coordinate either through nitrogen or through oxygen to a central metal atom. Similarly, SCN ion can coordinate through the sulfur or nitrogen atom. Next is coordination number. The coordination number of a metal ion in a complex can be defined as the number of ligand donor atoms to which the metal is directly bonded. For example, in the complex ion PtCl62 negative, the coordination number of platinum is 6. Similarly, in the complex ion FeC2O433 negative, the coordination number of Fe is 6. It is important to note here that coordination number of the central atom ion is determined only by the number of sigma bonds formed by the ligand with the central atom. Pi bonds, if formed between the ligand and the central atom, are not counted for the purpose. Next is coordination sphere. The central atom and the ligand attached to it are enclosed in square bracket and is collectively termed as coordination sphere. The ionizable groups are written outside the bracket and are called counter ions. Next is coordination polyhedron. The spatial arrangement of the ligand's atom, which are directly attached to the central atom, defines a coordination polyhedron about the central atom. The most common coordination polyhedra are octahedral, square planar, and tetrahedral. These are the shapes of different coordination polyhedra. M represents the central atom and L a unidendent ligand. Next is oxidation number of central atom. The oxidation number of the central atom in a complex is defined as the charge it would carry if all the ligands are removed along with the electron pair that are shared with the central atom. The oxidation number is represented by a Roman numeral in parentheses following the name of the coordination entity. Next is homoleptic and heteroleptic complexes. Complexes in which a metal is bound to only one kind of donor group are known as homoleptic. Complexes in which a metal is bound to more than one kind of donor group are known as heteroleptic. Next is nomenclature of coordination compounds. It is important in coordination chemistry because of the need to have an unambiguous method of describing formulas and writing systematic names. Particularly when dealing with isomers, the formulas and names adopted for coordination entities are based on the recommendation of the International Union of Pure and Applied Chemistry, that is IUPAC. Formulas of mononuclear coordination entities. The formula of a compound is a shorthand tool used to provide basic information about the constitution of the compound in an concise and convenient manner. Mononuclear coordination entities contain a single central metal atom. The following rules are applied while writing the formula. First, the central atom is listed first. Second, the ligands are then listed in alphabetical order. The placement of a ligand in the list does not depend on its charge. Third, polydendent ligands are also listed alphabetically. In case of abbreviated ligands, the first letter of the abbreviation is used to determine the position of the ligands in alphabetical order. Fourth, the formula for the entire coordination entity, whether charged or not, is enclosed in square bracket. When ligands are polyatomic, their formulas are enclosed in parentheses. Ligands abbreviation are also enclosed in parentheses. Fifth, there should be no space between the ligand and the metal within a coordination sphere. Sixth, when the formula of a charged coordination entity is to be written without that of the counter ion, the charge is indicated outside the square bracket as a right superscript with the number before the sign. Seventh, the charge of the cation is balanced by the charge of the anion. Next is naming of mononuclear coordination compounds. The name of the coordination compounds are derived by following the principle of additive nomenclature. Thus, the group that surround the central atom must be identified in the name. The rules are used The following rules are used when naming coordination compounds. First, the cation is named first in both positively or negatively charged coordination entity. Second, the ligands are named in an alphabetical order before the name of the central ion. Third, name of the anionic ligand end in O. Those of neutral and cationic ligands are the same except aqua for water, amine for ammonia, carbonyl for CO, and nitrosyl for NO. While writing the formula of coordination entity, they are enclosed in brackets. Fourth, prefix mono, di, tri, etc. are used to indicate the number of individual ligands in the coordination entity. When the name of the ligands include a numerical prefix, then the term bis, tris, tetrakis are used. The ligand to which they refer being placed in parentheses. Fifth, oxidation state of the metal in cation, anion, or neutral coordination entity is indicated by Roman numeral in parentheses. Sixth, if the complex ion is a cation, the metal is named same as the element. For example, cobalt in a complex cation is called cobalt and platinum is called platinum. If the complex ion is anion, the name of the metal ends with the suffix ate. For example, cobalt in an complex anion is called cobaltate. Seventh, the neutral complex molecule is named similar to that of the complex cation. For example, if we have to name CrNH3 3H2O3 square bracket closed Cl3, it is named as triamine triaqua chromium 3 chloride. Explanation: the complex ion